The piano is a very complex instrument with too many buttons, but it's simple to understand. Press a note, it makes a noise. Press it harder, it makes a louder noise. No matter, it has the unique properties to embellish harmony, create beautiful music, complex melodies, and by simply controlling your fingers to a inhumane level of dexterity. But how it relates to physics? Well, it doesn't. After some extensive research, in this video, we analyze the normal physics that is emitted by the piano. The piano was not the first of its kind to be invented. NANI?! There was a clavichord, harpsichord, and many other things that came before it into the 1700s, where a guy named Bartolomeo Cristofori designed one of the first pianos. Looking for ways to fix it, he showed Bach, which was not very taken lightly. Of course, it was not taken lightly. He had too many flaws and was in disadvantage compared to the other S-tier list of instruments. The developer of the piano was not very happy. Actually, he was depressed. But Bach gave him the code for him to improve the quality. But what exactly is the piano? It is very much like the harpsichord, but instead of plucking the string, you're hitting it with a hammer. In a nutshell, it's basically a harp with hammers attached to it. I will show this video animation not made by me and probably get copy strike to see how the piano works. It's basically you pulling down a lever that makes other levers do their job, that hits the key with very complex engineering within it. But this engineering somehow makes sense, and now you can hit the hammers with strings and using the physics engines to add collision. The piano today sounds completely different than it was a century or two ago, and it's also a factor how many musicians interpret music, as they have to know the limitations that the composer had when playing a piece. Before the piano became this very famous instrument that crushes people's head, it was not very well known back then. Nobody thought it was an instrument that was worth playing, not until that it was, and it pretty much is used everywhere. The reason why I chose the piano, because it is the instrument that represents the most physics and is also considered to be one of the most visual instruments. Many composers and musicians that do not play the piano at least know the basics of it, because the instrument literally shows you the chords and many other things that is easier to compose and do other things. So yeah, the piano is really good for that purpose and many others as well, and it's easier to explain in terms of physics and the other things come along with it. Everything about the piano is interesting, but it really doesn't explain about the relation with the physics. I have no clue what physics is, but I'll let Xavier explain.
Now, I don't know why DJ thinks I know the definition of physics, but I do know who knows the definition of physics, and that's our old trusty tool, Google. So I'm going to read the definition. Physics is the natural science that studies matter, its motion and behavior through space and time, and the related entities of energy and force. Physics is one of the most fundamental scientific disciplines, and its main goal is to understand how the universe behaves. And a lot of things in science is to try to understand how things work and function. So that's the definition of physics. As DJ said, the piano works by hitting the string thing to create vibration. The hammer that hits the strings connected both ends cause a vibration in the strings. The vibration is basically moving to a fixed point back and forth, which causes disturbance in the air particles in the atmosphere. Just like you hear me speaking, the tiny particles are actually the things doing the work to transfer it to your ear. How to measure the vibration thing? Well, as we discussed in physics class, the number of times it vibrates in a second is frequency, measured in hertz. As you know, hertz is measured with an equation. So the frequency determines how long or short the wave is. And the length of the wave determines the note's pitch. So basically, the frequency is what determines the pitch of the notes. And yes, there is an equation for that. With some complex rearrangement of variables, we can see how long the wavelength is. Let's say DJ plays the note C, even though he sounds awful. We can plug it into the equation to find out that wave is about 1 meter long. Keep in mind that it doesn't matter how big and low the wave is, as long as it's consistent with the wavelength. DJ can play a note hard or soft, but it still sounds the same. It's the same note. But why is it possible to do that?
Hey!
The amplitude of the note is what allows the note to be soft or hard. But this is not always true. The amplitude just measures how big the wave thing is. But how you view the note is just a subjection. Okay, just think like this. If I press a note hard enough, Chopin would think it's loud. Meanwhile, Beethoven wouldn't hear it at all. So amplitude is not equal to how loud the note is, but how the wave shape thing is looking. Now picture this. DJ has two pianos and he has nothing better to do with his life, so he's gonna play the same note on two different pianos. Is the sound twice as big? No. It's only a little bit louder because the wave sometimes crashes with each other and cancel each other out. It's because of the standing waves. But we're gonna talk about that later.
But I'm not done yet.
If you play a note really low on a piano or high on a piano, it will sound low compared to the middle notes because our brain just avoids low or high notes. That's why we can barely hear a bass player even though he's playing at the same loudness. Now, how do we measure amplitude? Through decibels. Decibels just compares the intensity of two sounds. That's how you know. Notice one thing. When DJ plays a sustained note, that sound doesn't magically fade away. There are steps to how a note fades. The 4 steps is called envelope. And through a music producing stage, you can edit that stuff too. But here are the 4 steps. The first stage is called attack of the note. It basically is the initial hit of the note. The second step is decay, and that is right after the hit. The third step is sustain, where the note would just hold for a bit, and then it would disappear. Okay, so the waves from the piano is actually called trans waves. The wave is similar to a violin, guitar, harp, or any instrument that is connected with strings at both ends. So when a note is being played, the note would go on until the end of the string and bounce back into the beginning and repeat. So the string being plucked actually vibrates in many frequencies instead of one because the waves are going back and forth with each other and crashing instead of making one continuous sound. This wave creates a series called Overtone Series. The Overtone Series is basically standing in frequencies, but it adds a concept of harmonics. In a string instrument like a piano, but more related to a guitar and violin, harmonics is the ratio that is expressed between frequencies of two notes, which creates the very complex shape of waves with its node and antinode. The most important thing to take away is that this is the basis of how music is constructed. The overtone is basically what creates sound for each instrument. Because it messes up with the harmonics so bad that it creates its own distinct crashing and original sound. Just think that you have your own sim character and you're customizing it, right? There are already predetermined assets like the eyes, the hair, but you mess around with it to make it personal to you, your own character. That's how overtones work. Overtone and harmonics are the reason the pianos and other instruments have intervals and perfect intervals which sound nice to our ears. Basically, the harmonics creates this interval through a ratio of frequencies. For instance, 1 to 2 is the ratio creates an octave, which is a perfect interval. The pattern of ratios continues to create more intervals, but to simplify, the meaner the ratio looks, the more dissonant or not happy sounding it sounds. One of the most mean sounds used for car horns is commonly known as tritone, which is a ratio of 45/32. There you go. We have intervals that we can make music and chords, and all these spicy chords with complicated ratios to create music on the piano. I just want to say that all this information right here is a little bit confusing. And I'm not instrumental major, piano major, a pianist.
Unacceptable.
But yes, this is very confusing and very long and drawn out. But there's a correlation. There's a connection. If you are lost or confused, just remember that. Piano relates to physics because of the vibration that causes waves, where these waves are actually standing waves, where it creates a harmonic. These harmonics allows us to have overtones to create intervals and chords with very happy math equations, but that's the overall idea. And whoever thought it was a good idea to measure sound. Anyways, I really enjoyed this project. I want to say that there's a lot to take from here. It might be confusing at the end of the day, but I really want to say that this doesn't only connect to a piano connecting to physics, but more of sound connecting to physics. The piano is more of an example, right? This could apply to my microphone, our microphone, the quality of our microphone, the sound of our microphone, and even, as I said before in the beginning, me just talking into the microphone, me just speaking. And once you really understand that, it's really interesting how sound works. And being a person who's interested in sound engineering, I think that this really helped me a lot and really helped me understand. And I really hope you guys really enjoyed this video and this presentation. Oof.
My name is João Cunhunjian. I'm a concert classical guitarist based in the New York City metropolitan area. And I'm also a classical guitar and music theory faculty at Newark School of the Arts in Newark, New Jersey, and Lucy Moses, Diller Quayle, and Silver Music Schools in Manhattan. Intervals can be understood as the difference, the distance between two notes. For example, an A to a B, the note A to the note B is an interval of a second because it spans two letter name notes, A and B. So that's the interval of a second. A, C, that's a third. Well, those are compound intervals. Those are intervals that are larger. Well, when you stack two consecutive intervals of a third, you can build triads. Now, triads are three intervals of a third. Could be actually two intervals of a third that sound at the same time. You have A, and then the third C, and then that C to an E makes another third. And when you play all those notes, all those two thirds at the same time, those intervals make a chord. Well, a chord can already be understood as harmony, although we tend to use the term harmony to designate more generally speaking how simultaneous sounds are organized. Harmony usually refers to how chords are combined and chained to one another. A polyphony is the concomitance of two or more independent melodies. So by means of the counterpoint is the technique of combining. And when you do the combination, then you end up with a music that we say is polyphonical. Poly is many, phony is a sound, so several sounds. Well, chords and intervals, they won't necessarily create good music. To the same extent that bricks and cement won't necessarily build a nice house, right? They're just core elements, building blocks per se, used to compose music, and that could be done in a thoughtful and art way or not. Consonants are the intervals, the music intervals that will, acoustically speaking, will have no clash to one another. So if you see a wave of, say, this note, it will be something like this, and then an octave, the same sound but sang higher. The waves of sound will coincide mostly. But if you have, so we say that an octave, for instance, is an interval that is consonant. In fact, it's a perfect consonant. It's as consonant as you can get. On the other hand, you have dissonant intervals. That would, the waves of sound, if you put in a graphic, will have minimal points of simultaneity, so they will clash a lot. A very famous example is a tritone. So if I play a C and an F sharp, so it sounds harsh to the ear. In fact, in medieval times, this was called diablos in musica. You couldn't do it because it sounded like the devil. When you get to the 20th century, 21st century popular styles, then dissonance got loosened up.
Thanks for watching my video, and I really hope that you enjoyed my physics project, and make sure that
blood in my hand, they don't understand. I done when I came, when I killed again. Told by three, my prophecy imposed on me. Forced by my lady, can't even shower my heart. Shady, claiming the throne, murder just daily. Call me Macbeth, greedy for more. Death on my breath, vein of Cador. Blood in my veins, don't feel humane. Blood in my veins, can't feel the pain. Red everywhere, don't even care. Can't shed a tear, won't say a prayer. Staying so pure, promise so rare. Know that for sure, killing them dead. Command in my hand, right by my side. Dirty homicide, fade in your eyes. Suicide with a man's pride.